Hello statistics, and welcome back to the video lecture series on the normal distribution. Today we are going to be covering the last section of chapter 5, which is sampling distributions and something called the central limit theorem. So a sampling distribution basically happens when you take samples of size n repeatedly from the same population. So a sampling distribution is a probability distribution of a sample statistic that you get when you take samples of size n. So for example, let's say that you take samples of 20 out of a population and you take a whole bunch of samples of size 20 all from the same population, and you take, let's say, the sample mean of each of those samples. That is what is called a sampling distribution. And specifically in that scenario, if the sample statistic that you're looking at is a sample mean, it is called the sampling distribution of sample means. Now, every sample statistic has a sampling distribution. So for example, let's say you take samples of size 20 repeatedly out of the same population, and you get the sample standard deviation from each sample. That would be the sampling distribution of sample standard deviations. We are going to focus on the sampling distribution of sample means. So this is just a visual of what that entails. So this Venn diagram shows the rectangle is the population, and each circle is a sample of equal size. The circles are of equal size, so the samples should really all be of the same size. And this Venn diagram shows that you can take multiple samples of the same size from a population, and each individual sample has its own separate sample mean. So if you take sample number 1 out of the population, it has a sample mean, which I'm going to denote as x bar 1. If you take another sample, sample 2 out of the same population, it has a sample mean x bar 2. So each individual sample that you take out of the same population is going to have its own individual sample mean. And because these are samples, each sample mean individually is going to be different, or at least slightly different. So x bar 1 is going to be at least slightly different than x bar 2, for example. Now here are a couple properties of the sampling distribution of sample means. If you were to take the mean of each of these means, I know that's a little bit of a mouthful, but if you were to take each of these sample means and you were to find their average, so you take the mean of the sample means, that is going to be equal to the population mean. So the mean of the sample means, which we are going to denote as mu x bar, is equal to the population mean mu. Now, the standard deviation of those sample means is equal to the population standard deviation divided by the square root of that sample size. And this is also called the standard error. Standard error is a lot more concise than saying the standard deviation of the sample means. So standard error is equal to the population standard deviation divided by the square root of the sample size n. Now, the central limit theorem is a really important theorem that is really the basis of inferential statistics. And what it does is it establishes a relationship between the sampling distribution of sample means and the population from which those samples come from. So the central limit theorem is really in three main parts. And the first two parts really deal with what kind of samples you need to take from what kind of population in order for the sampling distribution of sample means to be a normal distribution. So for number one, if samples of size n are taken from a population and the sample size is greater than or equal to 30, that's actually really important. If samples of size greater than or equal to 30 are drawn from any population with a mean and mu and a standard deviation of sigma, then the sampling distribution of sample means is going to approximate a normal distribution. And this did say any population, so it doesn't matter if the population is normally distributed or not. If the sample sizes are at least 30, then it doesn't matter what population it came from. The sampling distribution of sample means is going to be approximately normal. Now for number two, if the population itself is already normally distributed, then the sampling distribution of sample means is automatically going to be normally distributed for any sample size n. So if you know the population is already normally distributed, such as men's and women's heights, for example, then it doesn't matter what sample size you take. Any sample size n taken from that population is going to be normally distributed because the population it came from was already normally distributed. Now, in either case, whether the sampling distribution came from a normal distribution or if it came from any generic population and the sample sizes were at least 30. If the sampling distribution of sample means is approximately normally distributed, it is going to have a mean equal to the mean of the sample means. So the population mean is going to equal the mean of the sample means. And the sampling distribution of sample means is going to have a standard deviation of the population standard deviation sigma divided by the square root of n. So here's that kind of wrapped up in more generic terms. If the population is normally distributed, then the sampling distribution of sample means is normally distributed for any sample size n. So I don't care if you take samples of size 5 out of this population. If the population itself is normally distributed, the sample means are automatically normally distributed as well. Now, if the population is not normally distributed, or if you have no clue if the population is normally distributed, then as long as your sample sizes are at least 30, then the sampling distribution of sample means is normally distributed. And also, the bigger the sample size, the stronger it's going to follow a normal distribution. 30 is like that cutoff point. So if your sample sizes are 30 or bigger, it doesn't matter what your population is. And it doesn't matter if you know if it's normally distributed or not. The sample means are going to be normally distributed. The bigger the sample size, the better the normal distribution. And in either case, the mean of the sample means is going to equal the population mean. And the standard deviation of the sample means, also known as standard error, is going to equal the population standard deviation divided by the square root of n. So here's just a visual illustration of all of that. If you have any population distribution, I don't care if it's normal or not, as long as your sample sizes are at least 30, then the sample means are going to follow a normal distribution with a mean that is equal to the mean of the sample means, and the standard deviation is sigma over square root of n. Now, if your population is already normally distributed, then it doesn't matter what your sample size is, the distribution of sample means is going to be normal with a mean equal to the mean of the sample means, and the standard deviation is sigma over square root of n. So let's actually use central limit theorem and interpret it in a context. So for example, let's say that cell phone bills for residents of a city have a population mean of $47 and a population standard deviation of $9. Let's try that again. So the population mean is $47 and the population standard deviation is equal to $9. Random samples of 100 cell phone bills are drawn from this population, and the mean of each sample is determined. So they're taking repeated samples of size 100 out of this population. We're going to find the mean and the standard deviation of the sampling distribution of sample means, and then we're going to sketch a graph of that sampling distribution. So the sampling distribution of sample means, as long as your sample sizes are at least 30, then it doesn't matter what population it came from. It doesn't matter if the population is normal or not, as long as the samples are at least 30. Now, if you take a look at this graph here, this graph is the population distribution of cell phone bills. It looks vaguely bell-shaped, but it does look a little lopsided. It does look a little skewed, for over here. So I would say that this is probably not a normal distribution, and nowhere in this paragraph did it say if it was a normal distribution, so we can't assume. So just because it looks vaguely bell-shaped, we haven't got a clue if this population is normal or not. But it's not going to matter if the population is normal or not because of the sample size. Sample sizes of 100 were taken out of this population. So even though we have no clue if this population is normal or not, and it probably is not normal, because the sample sizes are big are more than 30, then the sampling distribution of sample means is automatically going to be normal. So our sample means are going to have a normal distribution because our sample size was bigger than 30. So it doesn't matter what the population it came from was. Our sampling distribution of sample means is a normal distribution, which means it follows one of these symmetric and bell-shaped curves. Now the mean of that sampling distribution of sample means, so the mean of the sample means, is going to equal the population mean, which is going to be 47. So the sampling distribution of sample means is going to have a mean of $47. Now the standard deviation of those sample means is not going to be the same as the population standard deviation. These standard deviations of sample means, also called standard error, is going to be the population standard deviation divided by the square root of the sample size. Population standard deviation was given as 9. Sample size was given as 100, so 9 divided by the square root of 100 is 0.9. So what this means is that the sampling distribution of sample means is a normal distribution with a mean of $47 and a standard deviation of 90 cents. So if we were to actually draw this sampling distribution, one standard deviation above the mean would be a cell phone bill that is $47.90. Two standard deviations above the mean would be a cell phone bill that is $48.80. And 3 standard deviations above the mean would be a cell phone bill that is $49.70. Now, one standard deviation below the mean would be a cell phone bill that is $46.10. And then 2 standard deviations below the mean would be a cell phone bill that is $45.20. And then 3 standard deviations below the mean would be a cell phone bill that is $44.30. So this is the sampling distribution of sample means. It is a normal distribution because the sample sizes were greater than or equal to 30, so it doesn't matter what the population was. And it has a mean of $47 and a standard deviation of 90 cents. So this is another example of interpreting the central limit theorem. So let's say that the training heart rates of all 20-year-old athletes, so this is our population is 20-year-old athletes. The training heart rates of all 20-year-old athletes are normally distributed with a population mean of 135 beats per minute and a population standard deviation of 18 beats per minute. And this figure here is a graph of the population distribution. So this is the distribution for the population training heart rates. It has a mean of 135 beats per minute and a standard deviation of 18. Random samples of size 4 are drawn from this population, and the mean of each sample is determined. We're going to find the mean and the standard deviation of the sampling distribution of sample means, and then we're going to sketch a graph of the sampling distribution. Now let's start with whether the sampling distribution of sample means is a normal distribution. And at first glance it looks like no, it wouldn't be because these are really small samples. However, that may not matter if the population itself is normally distributed. The training heart rates of all 20-year-old athletes are already normally distributed. So this population here is already a normal distribution. Central limit theorem says that if the population itself is a normal distribution, then the sampling distribution of sample means is automatically a normal distribution for any sample size, no matter how big or small. So because the population is normally distributed, it doesn't matter that the sample sizes are so small. The sampling distribution of sample means is also going to be a normal distribution. The mean of the sample means is going to be equal to the population mean. So the mean of the sample means is going to equal the population mean, which was 135 beats per minute. So the mean of the sampling distribution of sample means is going to be 135. Now the standard deviation of the sample means is going to equal the population standard deviation over the square root of n. So that is going to be 18 divided by the square root of 4, which is 9 beats per minute. So the sampling distribution of sample means is going to have a mean of 135 beats per minute with a standard deviation of 9 beats per minute. So a heart rate 1 standard deviation above the mean would be 144 beats per minute. 2 standard deviations above the mean would be a training heart rate of 153 beats per minute. 3 standard deviations above the mean would be a training heart rate of 162 beats per minute. 1 standard deviation below the mean would be a training heart rate of 126 beats per minute. 2 standard deviations below the mean would be a training heart rate of 117 beats per minute. And then 3 standard deviations below the mean would be a training heart rate of 108 beats per minute. So this is what the sampling distribution of sample means is going to look like. It is a normal distribution with a mean of 135 and a standard deviation of 9. And the reason that the sample means is a normal distribution is because the population itself was a normal distribution. Now, we've worked a lot with the normal distribution and probabilities in this chapter. So what we can use the central limit theorem for is finding the probability that a randomly selected mean will fall in a given interval of the mean of that sampling distribution. So just to put it in context, the first couple sections of this chapter, we looked at problems that involved find the probability that a randomly selected individual has a value in a given interval. What we can use the central limit theorem for is find the probability that the mean of a randomly selected group of people has a mean in a given interval. So this is going to be a little bit different. The overall idea is still going to be the same. We are going to be using our standard normal tables, we're going to be using z-scores, and we're going to be finding the areas to the left, to the right, and between. The difference is these problems are going to involve find the probability that a group has a mean in a given interval. So you do have to take the size of the group into account. So the z-score formula that you guys learned in the prior deals with individuals. So individuals, find the probability that a randomly selected individual has a value in this interval is x minus the mean over sigma. But if you are looking at a group, if you're finding the probability that a group has a mean in a given interval, the group size does need to be taken into account. So the z-score formula is going to be a little bit different. So the z-score formula is going to be the sample mean in question minus the population mean divided by the standard error. And if you remember, standard error is population standard deviation divided by the square root of the sample size. I would highly recommend you put parentheses around both the numerator and the denominator when you're calculating the z-score. You can plug it all into a calculator all at once as long as you have parentheses around both the numerator and the denominator. That's extremely important that you put parentheses around that denominator. So this is an example of a situation where you would use z-scores with the probability of a group having a mean in a certain interval. So what this graph shows is the length of time that people spend driving each day, and it is broken down by age. You randomly select 50 drivers in the 15 to 19 age group. So this 25 minutes is the population mean for all drivers aged 15 to 19. You randomly select 50 drivers from this age group. What is the probability that the mean time that they spend driving is between 24.7 and 25.5 minutes? And we're going to assume that the population standard deviation is 1.5 minutes. So note how this is a little bit different than the other probability problems that we have done earlier in this chapter. Earlier in this chapter, we would have been asked to find the probability that a randomly selected 15-year-old driver spends between 24.7 and 25.5 minutes driving. This is a little bit different. We've randomly selected 50 drivers. Find the probability that their mean time is between 24.7 and 25.5 minutes. So instead of asking for the probability of an individual spending this time driving, we're finding the probability that a group of 50 drivers has an average time in this time interval. So we are finding the probability that the sample mean of this 50 is between 24.7 minutes and 25.5 minutes. So this is actually asking for a group rather than an individual. Find the probability that this group of 50 has a mean driving time between 24.7 minutes and 25.5 minutes. So the overall concept is going to be the same. We're going to take each X bar value, 24.7 and 25.5, and we're going to turn each of them into a z-score using this modified z-score formula, because we're not looking for an individual driver, we're looking at a group of 50 drivers. So n in this case is going to be 50, the size of the sample. So the z-score that goes with 24.7 is going to be the sample mean in question, 24.7, minus the population mean, which was given to us as 25 minutes, divided by the population standard deviation, 1.5, over the square root of the sample size, square root of 50. And as long as you put parentheses around both the numerator and the denominator, you should be able to plug all of this into a calculator all at once. Remember, all z-scores need to be rounded to 2 decimal places, so you get negative 1.41. Then immediately you're going to look up negative 1.41 in the standard normal table, and you get a table value of 0.0793. Then we're going to do the same thing with X bar equals 25.5. We're going to turn it into a z-score using the z-score formula for groups. So since this is a group of 50, we need to use the z-score formula for a group. So the z-score that goes with 25.5 is going to be the sample mean in question, 25.5, minus the population mean, 25, divided by the population standard deviation, 1.5, divided by the square root of 50. And if you plug all of that into a calculator all at once with parentheses around both the numerator and denominator, you get negative 2.36. Sorry, you get positive 2.36, excuse me. So then if you look this up in the table, if you look up 2.36 in the standard normal table, you get a table value of 0.9909. Then, just like before, to find the probability that X bar is between these two values, you're going to take the bigger table value, 0.9909, subtract the smaller table value, 0.0793, and that is going to give you the area in between, which is 0.9116. So to interpret this in context, that means there is a 91.16% chance that the randomly selected 50 drivers have a mean driving time between 24.7 minutes and 25.5 minutes. So you can also say that 91% of all drivers have a mean driving time between 24.7 and 25.5 minutes. So see how this is a little bit different than the individuals. This is the probability that these 50 drivers have a mean driving time between 24.7 minutes and 25.5 minutes. So I want you guys to try this one for yourself. So I want you guys to first figure out whether this problem is dealing with an individual or a group. And then I want you guys to find the probability that, I want you guys to then work through this problem and find the probability in the question. So take a few minutes, pause the video, and resume when you are done working. Okay, so the mean room and board expenses at four-year colleges is $9,126. That is the population mean. So the population mean is given as 9,126. You randomly select 9 four-year colleges. So you have randomly selected 9 colleges. Now, in the last example, your sample size was 50. So it really didn't matter whether your population was normally distributed or not. Because the sample size was bigger than 30, you knew that your sampling distribution of sample means was automatically a normal distribution just because the sample size was big enough. In this one, we're going to have to be very careful because we've only selected 9 four-year colleges. So the only way with a sample size that small that our sampling distribution of sample means is going to be a normal distribution is if the population itself is normally distributed. So here, didn't really matter if the population was normal or not because we had a big sample size of bigger than 30. Here, we're going to have to be careful. So you have randomly selected 9 four-year colleges. What is the probability that their mean room and board expense is less than $9,400? And we're going to assume that the room and board expenses of all four-year colleges are normally distributed with a population standard deviation of 1,500. So the population itself is normally distributed. That means it doesn't matter how small our sample size is, the sampling distribution of sample means is automatically a normal distribution. So we don't have to worry about that. But let's figure out if this is an individual or a group. You have randomly selected 9 colleges. What is the probability that their mean room and board is less than 9,400? So you're finding the probability that these 9 colleges have a mean room and board of less than 9,400. So this is dealing with a group rather than an individual. This question is not asking what's the probability that a randomly selected individual college has room and board less than 9,400. This is saying what is the probability that these 9 colleges have a mean of less than 9,400. So this is dealing with a group. Specifically, where you're looking at the probability that that sample mean is less than 9,400. So you're finding the probability that these 9 colleges, their sample mean is less than 9,400. So let's use the z-score formula for groups. So the z-score formula for groups, we're going to take 9,400 and turn it into a z-score. So it is going to be x bar 9,400 minus the population mean 9,126 divided by, let's try that again. I'm sorry about that. So the z-score that goes with 9,400 is going to be the sample mean in question, 9,400, minus the population mean, 9,126, divided by the population standard deviation, which they gave us is 1,500, divided by the square root of the sample size, square root of 9. Parentheses around numerator and denominator, you should get a z-score of approximately 0.55. So then you're going to look up 0.55 in the standard normal table. So if you look up a z-score of 0.55 in the standard normal table, you get a table value of 0.7088. And because this is a less than probability, it is asking us for the area to the left. Just to reiterate, what area does the table always give you? It always gives you area to the left. So since we were looking for area to the left and the table value is the area to the left, we are done. So there is a 70.88% chance that these 9 colleges have a mean room and board of less than $9,400. You can also interpret this as about 71% of all samples of size 9 will have a mean room and board of less than $9,400. So this is an important distinction. The individual versus the group. For individuals, if you're finding the probability that a randomly selected individual, hold on, I don't know what I did. There we go. So if you're finding the probability that a randomly selected individual has a value that lies in a given interval, you are going to use the z-score formula, x minus the mean over the standard deviation. However, for groups, if you are looking for the probability that a group of size n has a sample mean in a given interval, you use the z-score formula for groups, which is x bar minus the mean divided by sigma over the square root of n. So it is really important that in any questions, such as exam questions, which this will be on the second exam, you distinguish whether this is talking about an individual or a group, because that will determine which z-score formula you use. So this problem right here is going to kind of illustrate that important distinction. So let's say that the average credit card debt carried by all undergraduates is normally distributed. So this means that the population of undergraduates have credit card debt that is normally distributed. So the population is already normally distributed. Because the population is normally distributed, that means the sampling distribution of sample means for any sample size is automatically normally distributed. Now the population mean is $3,173 and the population standard deviation is $1,120. For number 1, what is the probability that a randomly selected undergraduate credit card holder has a credit card balance less than $2,700? So we are finding the probability that a single randomly selected undergraduate has a credit card balance less than $2,700. So this is asking for an individual. Find the probability that this one randomly selected undergraduate X has a credit card balance less than $2,700. So because this is an individual, we're going to go through the z-score process and we're going to use the z-score formula for individuals. So the z-score formula that would go with this individual of $2,700 would be z equals 2,700 minus the population mean 3,173 divided by the standard deviation 1120. Giving us a z-score of approximately negative 0.42. Then we're going to look this up in the standard normal table. The standard normal table will give us a table value of 0.3372. So there's about a 33.72% chance that a randomly selected undergraduate has a credit card balance of less than $2,700. It's not a terrible probability, it's not that likely, but it's not a terrible probability. But we're going to contrast that with number 2. For number 2, you randomly select 25 undergraduates. What is the probability that their mean credit card balance is less than $2,700? So we're dealing with the same $2,700, but notice how this question is worded a little bit differently. You've randomly selected 25 undergraduates. We're finding the probability that their mean is less than 2,700. So finding the probability that a group of 25 has a mean credit card balance less than 2,700. So this is dealing with a group. We're finding the probability that this group of 25 has an average credit card balance less than 2,700. So we're finding the probability that X bar is less than 2,700 for this group of 25. So we're going to use the z-score formula for groups, which is going to be the sample mean, 2,700, minus the population mean, 3,173, divided by population standard deviation, 1120, divided by the square root of the sample size. Sample size is 25. And that gives you a z-score of negative 2.11. So already, even though we're dealing with the same 2,700, as soon as we're dealing with a group of 25 versus an individual, our z-score is already different. And if you look this up in the standard normal table, you get a table value of 0.0174. Which, since this is less than, the area to the left is your probability. So there's a 1.74% chance that the group of 25 has a mean credit card balance less than 2,700, which is a very different probability and a very unlikely scenario. So to kind of compare these two, The probability that one singular individual undergraduate having a credit card balance less than 2,700 is about 33%. Actually more like 34%. So it's about a 34% chance that the individual has a credit card balance, has this credit card balance. Whereas if you look at a group of 25, the chance that that group of 25 has a credit card balance less than 2,700 is less than 2%. So there's a less than 2% chance that the group of 25 has an average less than 2,700, which is much more unlikely and much more unusual. So notice those important distinctions on any exam questions. Make sure that you are very carefully reading through the problem and determining whether the problem is talking about an individual or a group. If it's talking about a group, the group size, the sample size does need to be given. So just be on the lookout for that, because these are very important distinctions. And as you noticed, very different probabilities. So that is going to be it for Chapter 5, and that is going to be it for your second exam. So your second exam is going to cover all of Chapter 4 and all of Chapter 5. So thank you all very much for watching, and I will see you guys in the next video when we start confidence intervals, which is going to be after the second exam. So thank you all very much for watching, and I will see you in the next video. Bye-bye.